Hello, Cyprien here. Now, in this video, let's talk about the different types of boundary conditions that you'll find in OnScale. So I'll be talking about the boundary conditions for structural and acoustics, um, and there are also additional boundary conditions for thermal, for electromagnetics, but this is beyond the scope of those lessons, so I will only talk about those few boundary conditions. Um, so those are the main boundary types of boundary conditions that you'll find in the most general type of simulations you'll do with OnScale. Uh, so the sim is for symmetry, and it means that there will be no motion across the plane. There's the fixed, which will refer to all nodes fixed, and also, of course, no motion. So this is a structural kind of boundary conditions. This one, symmetry, can be structural and acoustics. Um, and absorb impedance will be acoustics because they are all absorbing boundary for the waves. I'll talk about the difference between absorb and impedance right after. Then you have velocity, prescribed velocity to a certain set of nodes, and you have the free boundary conditions where nodes are free to move and which also assume void boundary. So when I say that those are for structural and acoustic, I'm not really making any distinction between acoustics and structural because OnScale considers both types of simulation at the same time. So each of those boundary conditions can be used both in structural and acoustics because those two types of analysis are totally coupled in OnScale. So each element has both structural and acoustic boundary conditions. Now, in addition to that, you have also some periodic boundary conditions that I'll talk about at the end, which can be defined with the bound comment. So let's talk briefly about the difference between impedance and absorb boundary conditions. So absorb boundary conditions are actually a bit more advanced than impedance. So what absorb boundary conditions are doing is that they are absorbing the energy at the boundaries. So both for elastic and acoustic materials, linear, nonlinear waves, and also for multiple materials on the same boundary conditions. And this works for broadband signals and varying angles of incidence as well. The impedance boundary condition is the way it's applied is a bit different. It's applied through the assignment of mass and stiffness value of an infinite load of a given material on a certain boundary of the model. And this can absorb the incident waves. And when I say incident wave, I mean the plane waves across a reasonable frequency range, which is 300% of the fractional bandwidth. But it's a bit lower performance than the absorb under certain conditions. But in general, the advantage is that it's more stable. So what happens is that in some cases, your absorb boundary condition might cause your analysis to diverge. So if you have this kind of problem, or you see that the divergence of your simulation is happening because of the absorb condition just changed to impedance, and this is much more stable. So in general, this will solve your convergence problems. Now, those boundaries can both be used both for fluid and solids, and also for some of the waves types in elastic media will not be properly absorbed with the impedance condition. So you should be aware about that, about this limitation of the impedance, because it only works with normal incidence waves. So this is the difference between impedance and absorbing. So very important to understand that. Now let's talk about assigning the boundary conditions. So there are several ways to assign the boundary conditions in OnScale Analyst. So first of all, I like to talk a bit about the simplification of the model. And that's why we have a symmetrical type of boundary conditions. If you can simplify, if you can make your model symmetric, you should absolutely do that. So this is what it means. And so basically, you're just cutting your model in two, and this will help you to achieve the same results for a fraction of the computing time. So the way to do that is to use the first type of boundary condition. So those are the boundary conditions assigned to the size of the model. So if you look at your model like that, like a domain, so you have 6 sides to this: 1, 2, 3, and 4, and 5, and 6. So if you're on 2 dimension, you only have 4 sides, and in 3 dimension, you have 6 sides. So you can just say, okay, this is my side 1, my side 2. I will assign symmetry to this side, or I will assign absorbing to this whole side. So this is the first way. So we call that global domain boundary conditions. Now, the second way you might want to assign boundary condition is to a specific set of nodes. So in certain model shapes, like this one, you only want to assign the absorbing condition to a part of the model, so not the whole side, but just one part of the side. And this way, the way to assign a boundary condition is different. So let's see how this is different in the code. So the method 1 that I'll use here. So let's talk about the method 1 first, to assign the boundary to a side of the model. So if you think about your model like that with 6 sides, you have to use the bound side subcommand in order to assign the boundary. So generally, this looks like this: bound side 1, and then the type of the boundary condition, which is sim here for symmetry. And what you can do also is that instead of calling those numbers, because it's not very descriptive, and you always forget which number is which face, so you can use the location of those faces. So instead of saying 1, 2, 3, 4, 5, 6, you call that x min, x max, y min, y max, and z min, z max. So you can write that bound side x min sim. So it's exactly the same thing. And so in practice, when you do simulation, you have to constrain all the faces. So you can add some side comments like that, one below another, and just apply the type of boundary condition, the boundary that you want to apply. Let's talk about the method number 2. So first of all, unless otherwise specified, all nodes on the boundary are assigned as free or in constraint. So you should be aware of that. Now, if you want to apply a boundary to a special side or a part of the side, then you cannot use the bound side because it only selects one part. So you have to use instead bound definition and bound node to specify the boundary condition to one part of the site. So how do you do that? Well, this is, for example, how you would define this kind of code for the small. So if you look at small, you have some key points. So this edge here is defined from the key point y2 to y3, and it's along the key point j2. So when you write, so those are the domain global boundary conditions, and in the second step, this is the local boundary condition just for this side. So first, I'm giving it a name called Constraint 1. This is the type of the boundary which is absorbed, and then I give it a node, and the space here, the location of this nodes is defined by those key points. So I remind you that the key points are some kind of variable which contains the number of the element which it is located at this position of the edge. So you have a grid, and the element which is here has a certain number, so which is saved into key points, and that those key points will allow you to locate this position. So I'll show how to actually perform that in an example in a video after that. Now, if you're interested to, instead of using key point, using location, geometry location, so you can use this type of syntax. So you define, for example, some geometry variables, then use those to function a CLS node, which will take the location as input and which will create those variables which are corresponding to the key points of those location, and then you can use that to feed the node subcommand to define the position of this boundary. Now, so briefly about the periodic boundaries in OnScale. So this is defined by a command called bond. So it's not inside the bound. It's a new command which has a set of subcommands that are required. So the first is def_n. Then you have course, fine, and end. So the bond def_n is the definition of the new bonded interface. So this corresponds to the name of this, and those are additional parameters. So I wrote here what those parameters do, so you can stop the video and have a look at that. But anyway, all that is written into documentation. So you just right-click, go to documentation, and have a look, and you'll see what this do. And those are parameters to define the more coarsely discretized surface being bonded and the more finely discretized surface being bonded together. So you can use those two to define the periodic boundary. And that's all for this video. So I'll have an example in the next video to show you how to generate quickly a designer model and have a look at in how it actually writes in the code the boundary conditions, so you can understand a bit better how this works.